All right, so here we are with chapter 10. Again, normally in class we would be doing the polyhedron activity, but since we do not have the ability to have those supplies right now, we are doing the 10-1, chapter 10 and chapter 11 as we would have traditionally. So these are the note sheets. You can, of course, find the copy of this on HeadRush, or you can just follow along. This section is going to be hopefully pretty basic, especially if you paid attention during your magic circle project. So some assumed formulas that you are supposed to know by now, including a few below as well, are a rectangle area. So there are a lot of ways that people write this. So rectangle area sometimes is mentioned as length times width, but we will start with base and height in these ones. And so the area of our rectangle is going to be taking the length of this base and multiplying by the height. So the area is going to be mentioned as b times h. Again, length and width are sometimes mentioned, okay? But in this case, we are going to go with base and height because it's used in basically every formula after this. So, whereas length and width are not. So, in that case, then if we want our perimeter, remember perimeter is the distance around an object. And so in that case, we're going to have a base plus a height plus another base, because up here is a base as well, and then plus another height. And so they tend to mention this as P for perimeter, and the fact that you're going to take two of the bases and two of the heights and add them together. So again, something that you can intuitively figure out, but technically there is a formula for it. All right, the next one here is our square, and the idea with a square, which is weird since we just said base and height for the rectangle, is that we can actually get more simplified and say that it's S for your side length. But of course, you can always convert back to the rectangle formula when you're talking about squares. So either way, for an area of a square, they love to talk about how you are going to take side times side. And because it's the same thing, they actually call it side squared. Okay, so again, that is an S, not a 5. All right, and then your perimeter is going to be S plus S plus S plus S. And so all of those S's combined means that your perimeter is 4 S's. All right, so those are, again, assumed formulas that you know, and then we're going to reference them. The first main idea here in our notes is the area addition postulate, and I'm pretty sure you figured out by now that you could add areas together, but the definition says here that the area of a region is equal to the sum of the area of its non-overlapping parts. So if you've ever done that game Tangrams, which is more like a solitaire game, what happens is they take this square and they break up your square into a tiny little square, two of these same right triangles, two of these same larger right triangles, kind of a medium right triangle, and then this parallelogram here. So the idea is that you could, if you felt like it, break up any square into these 7 pieces, and you would be able to find the area by adding each of them together. So again, just add all of the areas together is the main idea here. And this will come into play a lot more later when we get into non-regular shapes. But we're talking about shapes with names at this point. So the first shape that we will be talking about, other than, of course, a rectangle and a square, is another 4-sided shape, and that's going to be our parallelogram. And it turns out that a parallelogram area is actually going to be base times height as well. Okay, so the idea, especially if you take into account this piece here, is that you are actually taking this piece and moving it over here. And so we're going to put that height there and that base that was here. And if you move it over, we now actually have a rectangle. And so because it makes a rectangle, we in fact have the rectangle formula. Okay. Just double check though that you understand that this height is actually what meets at 90 degrees. Okay, so you want the distance between those two parallel sides versus this side length. Okay, so just to double check, we want to write that this is not the height for this diagonal piece. All right, then we have a few examples, and as I mentioned previously, the ideas in here are not going to be as basic as the geometry that you have had already. So they will not, for instance, say, find the perimeter of this square. They will say the perimeter of this square is, and then they want you to work backwards and find the side. They might also, instead of telling you that the side is S, they might say it's 4x plus 2. Okay, and so there will be some algebra put in there and also the algebra of working backwards. So, of course, I am telling you that as we do our first example here, which is to find the area of the parallelogram anyway. So, taking a look at this first parallelogram, we have a lot of things going on, but you'll notice that instead of just giving the base and the height, which is what we need in the area of a parallelogram, we are only given the base, which is 6, and then we have to do kind of a side problem in order to find the height. In fact, hopefully you've noticed that this is in fact a right triangle, which involves the height. And we have this other leg value of 3 and this hypotenuse of 5. And so we're going to use the Pythagorean theorem in order to find out what the height is. So we will apply some variables here. So this could be our A value in the Pythagorean theorem. This could be our B, and since this is the longest side, that would be our C. And so we're going to use the Pythagorean theorem of A squared plus B squared equals C squared in order to find out what our height is. So again, A is H, so H squared, B is 3, and C is 5. And so now we work backwards. 9 is 3 squared, 25 is 5 squared, but then we can subtract that 9 over to be with the other number. And so we realize that we have H squared, which we will take the square root of to get a height of 4. So we now have a base of 6 and a height of 4 based on the Pythagorean theorem. And now we can plug it into our formula. So we have 6 as our base, which is interesting because my B's look like 6's anyway. And then a 4 for our H. So that means our area is 24. Another thing that we're going to have to remind ourselves here is that we are now talking about area and we were given units. So make sure that you also have inches and then the fact that it's area, so squared. So that is our parallelogram area. And again, we were not given directly the base and the height. We had to find the height by Pythagorean theorem and then use our formula. So again, usually most of these will have 2 steps in them. All right. Our next example here says that we need to find the measure of the height of a rectangle in which the base is 5, and the area here, as I mentioned before, is this interesting formula. So going back to what we do know, we know that the area of a rectangle is the base times the height. And so they said that the B is 5, and they've also said that the A is this intense thing right here. So that means that instead of an A, I can write 5x squared minus 5x. Instead of a B, I can write a 5. And then our H is over here. So that means that what we need to do is actually work backwards in order to find our H all by itself. So we're going to go ahead and divide everything by 5. And if we divide both sides by 5, that means both of these pieces are divided by 5, which means 5 divided by 5 will just leave us with x squared. Negative 5 divided by 5 leaves you with negative x, and that equals your h. And so again, we were given an area that was less than satisfying because it is not just a regular number. And so we are going to be given a height in that case that is also not necessarily just a number. And so in that case, your height is going to be, and the way they wrote it was in parentheses, but x squared minus h. We also want to double check because notice we're trying to find a height, which is a length, and we're using centimeters. So make sure that you also have your units. And again, not squared because it's just a height to length. All right, then moving on, we're going to find the perimeter of the rectangle. And again, they're giving us the area. So in that case, we're going to have to find out what this missing piece is here in order to get our length that we will then put into our perimeter for rectangle formula. So the perimeter for a rectangle, remember, is 2 bases plus 2 heights. And we are given that the height is 6, but we do not know what the base is. However, we do know that the area of a rectangle is base times height, and we are giving area. Area in this case is 12x, so we can fill that in for A. And then again, we also have that the height is 6, so we can fill that in. All right. Very unfortunate that my B's look like 6s. So we're going to divide by 6 to both sides. And so 12 divided by 6 leaves us with a 2. And of course the x comes with. And then our 6's cancel. And so that just leaves us with the base. So we now know that our base is 2x. And so now we can fill that into our formula up here for perimeter. So perimeter is going to be 2 times the base, which is 2x, plus 2 times the height, which is 6. And so we're going to get 4 x's for this first term, plus 12 for the perimeter. And so our answer is 4x plus 12. And again, we do have a unit. In this case, it's feet. And since we are finding a perimeter is a length, so it is not squared. Alrighty, then we move on to a different formula of in this case, actually a 3-sided shape. So your area of a triangle. Hopefully the way that you've thought of area of a triangle is base times height over 2. You can think of it as a half base height, and you can think of it as 0.5 base height, but the idea is that you are actually going to take the rectangle that exists. We will make it, I like it to be made like this. And so this triangle and this triangle are the same. This triangle and this triangle are the same. So if we actually did the height, which would be this piece, and the base, which is still this whole piece here, we could do base times height like any other rectangle for area. But then, of course, we don't want this piece or this piece. So we have to cut it in half. So again, the area formula is base times height, but then cut in half. So divided by 2. All right. Same thing goes for what's happening here, okay? The problem, however, is that we do not actually have a triangle, but we almost have a triangle. So we're imagining that this continues on. And then in that case, we would be able to take this base times this height, which we don't quite have, right? We only have the distance from here to here as the height. And so we are going to end up taking a half of that because we're taking this piece out here. It's actually easier, other than looking at it as a triangle, if you look at it as, this is going to be hard to draw on top of here, an extra trapezoid. So if we think of this as an extra trapezoid, this is base 1 now, this piece over here. This is base 2 up here. And again, we still have this height. And remember that in a parallelogram, remember the base times the height is going to be the area. And so if we did this base, which is technically base 1 and base 2 added together. So if we do base 1 plus base 2 added together, multiply that value by the height, right? Base times the height. But then again, we don't want this piece, so divide that by 2. So that's your area formula for a trapezoid. it's taking two of those trapezoids together, multiplying it, making two, which makes a parallelogram, and then doing the parallelogram formula of the base times the height, but then divided by 2 because we don't want that piece. All right, so we're going to use these two ideas in the next few problems. So they want you to find the area of the trapezoid. They're telling you that base 1, that's what we call this upper base here, and base 2 are 12 and 9, and then the height is 3. So your area of your trapezoid, again, is the bases added together times the height divided by 2. And they gave us base 1 as 9, base 2 as 12, height of 3, and of course all of that divided by 2. Order of operations says to do what's in parentheses first, so we'll have 21 times 3 divided by 2. 21 times 3 is 63, which we're going to divide by 2. And so that means we have 31 and a half. All right, so 31 and a half, and notice all of them are in centimeters, and we are finding area. So 31.5 centimeters, as the others are, but then squared because it's area. All right, so that one was a little bit more of a forward movement. The next one here wants you to find the base of the triangle in which the area is this x squared idea. And so they want you to find this length here. So in order to find that length, we need to set up the triangle formula, which is going to be base times height divided by 2. We already know that area is x squared, so we can replace a with x squared. We're keeping b as base, but then this height is x. And so to solve, we can go ahead and multiply both sides by 2 because it's being divided by 2 and we want b by itself. So in that case, we're going to have 2x squareds equal to b times x. And then since we're again trying to get the b by itself, we're going to divide both sides by the only other thing other than b, which is x. Those will cancel and these almost cancel, but we're left with 1x still. And so 2x is going to equal our base. And remember that this is a distance, and they did tell us inches, so we do want to write inches and not inches squared. All right. The next one here, we want to find the measure of base 2, so that's one is here, of the trapezoid in which the area is 8 feet squared. All right. So again, area of a trapezoid formula, definitely want to be able to reference that. So b1 plus b2 times the height over 2. And we are given that b1 is 3. And we're also given that the height is 2. So we're going to fill in all the things that we know. So an 8 for A. b1 is 3. b2, again, we're trying to find. Our height is 2, and we're dividing by 2. So the first step that I'm going to do here is the fact that this thing in parentheses is being divided by 2 and multiplied by 2. So we can, in fact, cancel both of those, which gives us 8 equals 3 plus b2. And so in order to solve, we would just take away the positive 3 that's sitting there and get 5. So that means that 5 feet for the length is our length of the second base of this trapezoid. All right, so moving on to our last two formulas. Turns out they're pretty much the same. The formula for both of these is going to be an area of the diagonals multiplied. We're not going to call this base and height. However, if you actually take this triangle and move it up here, and this triangle and move it up here, we now have a rectangle. And of course, a rectangle is base times height, But the way that we get that piece on this diagram is we take this diagonal, which we're calling diagonal 3 or D3. Oh, sorry, D2, sorry. What did I call D1? I can't see from here. Oh, sorry, D1. And then this height here, which we call D2. And so we're going to do the height times the base. We're just calling them diagonals, or D1 and D2, because in a kite and a rhombus, those are more identifiable than a base and a height, especially since the base is technically going through, which doesn't seem like a base. So we switch our names from base times height, even though that's actually the same exact way that we calculate this. So in number 7, what we are given here is that the measure of D2, so the second diagonal, is what we want to find. And we're given that the first diagonal is 16 and the area is 48. So the area of your kite is going to come from diagonal 1 times diagonal 2. But remember, diagonal 1 was 16 and the area was 48. So if we plug in those values, 48 and 16, we can then solve by dividing by 16. And we get the fact that 3, for how many 16s go in, is our second diagonal. And of course we have a unit, so we're looking at centimeters for the length. All right. Our last 2 examples here again have to do with diagonals. So another word problem in number 8 without a diagram, that's fine. We need to find the area of a rhombus. And remember, area of a rhombus is just diagonal 1 times diagonal 2, or technically base times height. And the diagonals have these measures, 10x plus 10 inches and 6x plus 4 inches. So that means that we're finding area, but of course, instead of given standard things, we'll apply this one to be D1 and this one is D2. This says diagonals. And so we're going to take 10x plus 10 and end up multiplying that by 6x plus 4. Remember maybe from Algebra 1 that this is not actually just multiplying the way that it is here. We are actually going to be putting it into an area model or foiling, if that's what you did. And so in order to get 10x plus 10 into its polynomial format, we have to multiply each of these pieces. So 60x squared and 60x's, 40x's, and then 40. So that means that altogether we have 60x squared. These two come together to become 100x, and then the other 40. So our area is going to be this terribly long trinomial, so 60x squared plus 100x plus 40. And I'm going to apparently fit that on this tiny line. So thank you, me, for making that small. And then, of course, our units, which in this case are inches, and then we are doing area, so squared. To kind of make sure that we keep it all together, mostly they'll put these expressions in a set of parentheses. So we'll copy that. All right, then our last example in the notes here is to find the area of this kite. And remember that all kites are going to be the diagonal 1 times the diagonal 2. We're missing quite a few pieces in this diagonal, so we have to kind of convert back to when we did quadrilateral ideas. And so remember that 4-sided shapes, especially a kite in this case, meet at 90 degrees. And so technically what you have here is a bunch of Pythagorean theorem problems. So for instance, this upper triangle here has a hypotenuse of 41, a height of 9, and another leg of x. And so if we want to find out what x is, which we do because we need x plus y to be this diagonal, we're going to have to do the Pythagorean theorem. So the first thing that we're going to do is call this one C for the hypotenuse, this one A, and this one B. And so our A squared plus B squared is going to equal to C squared, but A is X, B is 9, and C is 41. And so if we solve this, we need 41 squared, which is 1,681. And that's going to equal 81 from 9 squared, plus X squared. So to solve, we'll subtract the 81. And we get X squared equal to 1,600. And so the square root of 1,600 is going to get us 40, which means that I'm going to take the square root and get an X of 40. So again, that means that this piece, other than equaling A, is also 40 for the distance that stops here. But then from the distance to here, we're going to use another Pythagorean theorem, but we're also going to use the idea that a kite has this segment and this segment that is bisected by this other diagonal. So that means that this is also 9 feet. So we're going to use this new triangle that has a C of 15, a leg length of Y, that we'll call A, and a leg length of B of 9. So that means that we're going to do A squared plus B squared equals C squared, but in this case A is Y, B is 9, and C is 15. So we're going to get 81 for 9 squared again. 15 squared, I believe, is 225, but I'll double check. Yep, and then we're going to subtract 81. And so y squared is going to be equal to 144, which of course is a perfect square of 12. So if we square root, we're going to get a y of 12. So now we know that y is c, but it's also 12. And so the one diagonal, diagonal 1, is going to equal 40 plus 12. And diagonal 2 is going to equal 9 plus 9. So now we can put those in for our diagonals in the area formula and get 52 times 18. So we have 936, which we will use as units of feet. And since we are doing an area, feet squared. Alrighty. So those are notes for chapter 10, section 1. Again, mainly four-sided shapes, except a triangle in there as well, and their areas and perimeters. So the homework will be a lot of the same, so kind of keep these formulas handy for reference.